Good day, ladies and gentlemen, and welcome back to our discussions on applied mathematics for economists. Today I'm going to introduce to you section 8, and that talks about an introduction to differential equations. We will look at the general solutions of a first order first degree differential equation. Now, this is the overview of what I intend discussing with you, and specifically we will look at differential equations, the solutions. We will now narrow our discussions down to, linear differential equations of first order first degree, and then going further, we will look at the general solution and how to deal with, solutions of this nature. The reference or the reading list is, as you can see. First of all, what is a differential equation? This is an equation that expresses an explicit or implicitly relation between a function, y equals f of x, and its derivative. So these are all examples of a differential equation, right? Because there is a derivative in there, and then you also have a function in there. So you have a mixture of derivatives and function. Then we call this one differential equations. Now, how do we identify differential equations? We use two things to identify a differential equation. The first one is the order, okay, which is determined by the order of the highest derivative in the equation, and then the degree, right, which is more or less the highest power to which the derivative of the highest order is raised. So if you look at this one, for example, we call this one a first order first degree differential equations because the highest, order is 1 here, and it is all raised to the power 1. This one, we call it a second order because the highest derivative is I, and it is raised to the power 2. And so we call it second order second degree differential equations. Now, there are two things that we also have to know. We have something we call ordinary differential equation and partial differential equation. When you have the independent variable being only in terms of one variable, in this case, the differential here is respect to x. So we call this one ordinary differential equation. In this situation, we have the independent variable in terms of x and y, right? And the dependent variable is z. So this one, we call it a partial differential equations. There are some examples here. I just want you to identify these, just name them as I just did, so that you'll be able to identify the two different types of differential equation. One thing we try to distinguish in differential equations is also the use of homogeneous or non-homogeneous differential equation. And if you look at this equation here, where you have a derivative here and then we have a function here, if this function is equal to 0, then we have a homogeneous differential equation. Otherwise, then it becomes a non-homogeneous differential equation. And another thing that we also need to discuss, which we are going to focus more on, is first order first degree differential equation, which is of this form. So what happens is that the highest degree is 1, which is also raised to the power 1. So we call this one first order first degree differential equations. Some examples are beginning over here. So this one, for example, you can name it first order first degree non-homogeneous differential equation because of the t that we have over here. And we can have the same thing that we have over here. And the question is that if we send this one here, it becomes t minus t plus, 3tx. And that is the function f of xt, which is not equal to 0. So this one becomes a first order first degree linear non-homogeneous differential equation. Now, what are we all interested in? We are interested in how to solve differential equations, right? Because we would like to apply it in economics. If we are talking about a solution of a differential equation, we are just interested in a sort of a function that does not contain a differential, a derivative or a differential, but then that function satisfies the differential equation. It's a little complex. Let's look at an example. If you look at this differential equation, for example, now if you want to, find a solution to this differential equation, what we do is that we integrate both sides. Okay, so we step it down, second order, differential equation. There's a constant here. We integrate it again. We, do it until we have a function here that does not contain a derivative or a differential equation. This becomes, the solution to this differential equation. It's a solution because when this equation satisfies what we have over here, simply when you differentiate this equation 3 times, you get 0, meaning that the equation satisfies our differential equation. One thing we also have to know is that this equation is a family of curves because we have B and C being constants. As soon as you change B, you change C. That is, if you are given boundary points, then this equation changes. It's a quadratic, all right, but you can get different quadratic, equations based on the value of what? B and C. Now, try your hands on these simple, activities, and then you understand a simple solution of a differential equation. Now, let's go further and talk about linear differential equation of the first degree of the first order. Now, this equation is of this form. Okay, I have specifically allowed here m of xy to be a function in 2 variables and then also a function in 2 variables. With simple sort of manipulations, we can more or less express this equation in this form. And one condition that we need to do is that these functions, right, m and n, they are all homogeneous of the same degree in x and y. Recall when we talk about homogeneity, what we mean. It means if we introduce any factor alpha here, the whole function will also more or less depend on that value of alpha. There's a simple example over here. So there's a homogeneous linear differential equation of the first order first degree, which you can reorganize in this form. Okay, and we would further go on and see how to solve this equation. Now, when you have a linear first order differential equation, some of them you can separate the variables, meaning that you can put all the x on one side, all the y on one side. In that case, if you can find a function f, which is equal to c, and such that that function will satisfy this equation, then that function becomes a solution of this differential equation. Let's look at an example. We have this equation over here as an example. I can reorganize it in this form. Notice that I have all the y's here, all the x here, meaning that I can separate the variables. Okay, so let's go further and try to solve this. I introduce my integral sign, integrate them, and I get something like this, right? And when we reorganize this equation, which is equal to c here, this is the function f of c, which is equal to a constant here, and this becomes the solution to this differential equation. And you can check it yourself. When you make y the subject of the formula in this equation, and you differentiate it and reorganize it, you are going to get what we have over here. Now, there is also another example here, but here, in order to get a very, sort of actual solution, I've introduced a boundary point. As I said earlier, in this equation, as soon as you change c, your equation changes, and you can decide to have a specific equation when you introduce a boundary point, as I've done over here. So, as usual, there's our equation here, which I have reduced it to this form, and when I rearrange them, I get something like this, right? Now, I've separated the variables, meaning that I can integrate both sides, okay? When I integrate this one here, x, what I mean is that what we have standing over here, we can rewrite in this form, okay? Rational functions, you recall we discussed that, and therefore, when we integrate this, we are going to get this solution. Now, so we have a solution of this nature, because of the boundary point, I find the c here, plug it back into our equation, and have this to be the solution of our differential first order, first degree linear differential equations. Please try your hands on these exercises. And then, now, what we want to know further, it's about, the homogeneity of this function m and n. When this function is homogeneous of the same degree, in some of the equations, we cannot solve them, but when we introduce another variable, let's say y equals v of x or x equals v of y, we will be able to reduce the function into a separable function, which we have just discussed, and be able to solve. What I'm saying is that if you have any first order, first degree linear differential equation, and the m and n are homogeneous of the same degree, then introducing a variable this way will permit you to reduce this equation into a separable equation that can easily be solved. Now, an example will really elaborate this. Look at this function. So more or less, this is my m of xy, there's my n. Okay, what you could see is that this function, the m and the n, they are all homogeneous of degree 2. Okay, you can cross-check yourself, meaning that if I introduce a function, y equals vx or x equals vy, I would be able to, solve that equation. Now, let's go further. So I introduce this function, y equals vx. When I take the total differential, I get this. I slot these values into my original equation. When I slot them and I deal with them, sort of simplify, I get an equation like this, right? Which boils down to an equation like this. You see, we have this equation more or less over here. They have been separable. They are separable because we have all the v in one additive, all the x in one additive. And this one, I've written it in this form just to enable us to integrate. And further, we have an equation of this nature, which we more or less integrate and get what we have over here. Notice that the v we have here from this equation, right, our v here is equal to y over x. So we come and plug the v into our equation, and then we have a solution of this nature, right? We have a solution of this nature, which when we go on and further simplify it, we have something like this. Please, again, try your hands on these ones using the formula that I've just discussed. Try to reduce them to a separable sort of equation and then solve it. There is some activities for you here. Now, having done all this, I would like to make things easier for you in the sense that we are going to find a general formula for trying to integrate or trying to find a solution of any first order, first degree linear differential equation. So you may not want to go back with all those long things that we've discussed. There's just a prepared formula, right? If you go to, Shom's series, he tries to prove this formula. But here, we just presented it for the sake of time so that you can use it. Now, in our first order first degree linear differential equation, we can always express it in this form. So this is our differential operator. And then we have p of x being a function of x multiplied by y. And this is the function that determines the homogeneity of our equation. Now, the general solution is given by what we have over here. And further, we can simplify to what we have over here just by expanding the exponential function, and then we get this sort of solution. Now, what I'm going to do is that these ones I know is going to be difficult for you to solve now just because I've not given you an example here. But I'll leave it to you. In our next sort of a lecture, we are going to apply, right? We are going to apply this formula. And once we've done that, I think it's going to be easier for you to more or less solve these equations. So don't worry yourself if you are not able to do that. Thank you very much.